Igor, is it too slow, too fast, too slow? The current pace?
No, it's good. No, it's good. I think. Well, we have had some experience with regression, and some of us had good examples in terms of clustering, but interesting. Yeah, interesting. So pace is good.
Okay. I planned this lecture as an equalizer, so it should be familiar to most of you. And this is just to bring everybody up to the same speed. And then we could dive into something that is less understandable, less known. But my plan is to stay on the same level of explanations, meaning that not using too many formulas per slide. This is my major principle, is not to overuse the math.
Well, thank you for that from my side. I think all guys they should appreciate this approach, but we may ask them, because heavy math will not help with understanding much.
Yeah. Somehow the heavy math never helped me. I was not bright enough for my side to understand all this math. So I'm happy not to torture my own students on that.
Mm-hmm.
Where are you? Are you in the office?
Yeah, I am in the office right now, but there is no one here in the office except me and several people. And actually, starting from 12th of May, we have some we obtained the chance just to visit office with all that, temperature measures and social distancing and so on. So actually, yeah, I may come to office just to complete my tasks or something like that. Because after the school, after our lectures, I'm going to have a status call for my project, so it's better to make it from office.
Gotcha. Understood. I plan to go back to our research building as well from next week and actually be in the office, but this week I'm still at home. Understood. Please ask questions, and as soon as you feel like there is something that you might be interested in not covering, then go ahead and just step in.
Okay, we'll do that.
Yeah, that's not compulsory. It's just if you feel like.
Thanks. Thank you.
And is Tartus, this is a city where chocolate produced? Because I know this from chocolate point of view.
Which one?
I think it's called some
No, I don't think it's the same one. We have Kaliev, but I don't think it's that one. We are famous. Well, we aren't famous. That's the full stop, I guess. But we have a famous semiotician who is now that I'm saying famous, I get this. Now I lose the name. I have a very bad memory of names. But he is basically, anyway, he's Russian, so he's more like a Russian semiotics type of school. We are very famous for the medical school that we have. So we are we have a large medical faculty, but I don't think we are famous for anything else than that. We have Estonia in general is famous for Jan Tallinn and Skype. So Jan Tallinn is the guy who invented Skype, and it was developed in Estonia.
Mm-hmm.
This is something that we are most famous for. Singing festivals, yeah, that kind of stuff, I think. but I'm Ukrainian, so I have been here for 8 years now, and I'm getting Estonian with every year that I spend here, but I'm still Ukrainian at my heart. So I do teach. I met Romanko exactly at the Kiev summer school that I have been organizing together with my friends from KPI. So we were studying at KPI, and then we felt that the education level was very, very bad. So we thought that this would be nice to get some external professors and lecturers to deliver talks, and Romankov was one of the first people that would come to our summer school and deliver talks at our summer school. And that's how we met with Alexander.
Okay.
But Tartu is a beautiful place, so if you would ever consider traveling, let me know. This is a place worth visiting. Tallinn has the largest European medieval center, which is preserved and which is defended, protected by UNESCO and all that kind of stuff. So pretty cool place.
Okay.
All right, so welcome back, everybody. I am hoping that you guys had some break. We will slowly get back to our digits classification. So I wanted to use MNIST, which is a large and very popular handwritten digits database. So MNIST is just, I guess some of you may have heard about MNIST. Very few people know what MNIST stands for. So MNIST is a modified National Institute of Standards and Technology database. And MNIST consists of 60,000 handwritten digits. And they are pretty small. Let's consider one of the examples. It's this kind of image. It's an image of 7. So as you probably know, matrices of that kind of stuff. So images are not stored as images, they're stored as matrices in the computer memory. So the matrix for the 7 looks like this. So this is a matrix of values from 0 to 255. So 0 represents black color and 255 represents white color. So the bigger the value of the intensity, the lighter the pixel, okay? We can color this matrix based on this color scale, and this is what we see, right? This is 7. This is what 7 looks like in matrix representation. This specific data set has digits of size 28 times 28. This is important because in machine learning, we are not operating with matrices. We operate with vectors. So we operate with instances. So one instance of this digit has 28 times 28 features, right? So each of the images has 768 features. Another important thing that this data set consists or has is the supervisor label. So we actually know what is written on this picture. So we have a supervisor who would say, hey, this is 7, right? So we would record for each digit, we would record a label. So we would know what is actually on this matrix 28 by 28. And you will see it's not very obvious. But some digits, it looks very unclear what is on the image. For example, this one is very curvy, and there are all sorts of weird digits that exist up there. So what happens is that we go to our collaboratory. So let me share my Google Chrome screen. So you guys should see my my Chrome screen, and you should see the supervised learning collaboratory, right? I know that you have, so please first do this file, save a copy and drive if you haven't done it before. So you should be able to edit the cells, right? So you should be able to write code inside cells. If you cannot write code into cells, then it means that there's some kind of small problem here and there. Let me know if you are fine. You can, by the way, you can raise your hand in Zoom. There is this, I'm host, so I can't raise a hand, but you can raise a hand if you click on participants list, and then there is an option to raise your hand. So if you've done it and you have no problems with editing the supervised learning.ipython, let me know it by either telling me or raising your hand. Okay, I can see Kenneth raise their hand, so cool, thank you very much. I can see it. Can you guys raise your hands if you are okay and the collaboratory is under your control? If you're if you have a power over your collaboratory, okay, somebody raised their thumb. Thank you.
And how to make this raise hand?
You go to the participants list.
Yes.
And then at the bottom of the participants list, you probably have some kind of raise your hand, or you can also click on reactions. I think there is also a way to do it with reactions. Again, I'm host.
Okay, okay. Now I see it. Yeah.
Okay, yeah, right. So Igor did it. He raised his big thumb. Now it's Oleg and Semyon. Lena, you did it as well. Cool. So thank you very much, all. I guess you mastered the collaboratory. You have had experience with collaboratories, which is great. There is a very short introduction just to make sure that you are on the same page. Collaboratory is basically a virtual machine running somewhere in California in some kind of Google servers. And this virtual machine has some RAM and it has some GPU. So you can go to runtime and you can change the runtime to make sure that you're using GPU. If you need a GPU, for example, for me, there is no GPU because I'm not using GPU, but you can still use it in case you need deep learning stuff. I think in this lecture, in this practice session, we don't need the deep learning stuff. And also you need to know that this collaboratory runs Ubuntu underneath, and you can make Linux commands by typing ! and then the Ubuntu command, regular Linux command. So you can type, for example, ls, and you can see what is inside your virtual machine. Now that it's done, we can go to the keyinit. So we will implement k-nearest neighbor on MNeast. But before we do it, we will need to do some setup. So please follow me and run this cells one by one as I do. So we will now do this live coding together with you. All right, so I'll run the cell. So I ran the setup cell. It has NumPy library, Pandas library, Matplotlib library, some operating system libraries. We also would need TensorFlow just to get access to MNeast. We also use 1x TensorFlow because some of the commands that I'm using, they are deprecated in the new version. So we need to explicitly say that I need TensorFlow version 1. And this line here, it just takes the MNeast and reads in the MNeast. It actually downloads MNeast to your virtual machine, and you can see how large is the data set by number of bytes that each file has. So now if I run ls on my computer, I can see MNeast being part of this, right? So now I have downloaded MNeast to my virtual collaboratory machine. Anybody, do you guys have questions? Anybody has questions? Just shoot them straight away. As soon as you have a question, just don't wait, just go ahead. So now this is what I was saying. We are not operating with 28 by 28. We convert these 28 by 28 images into 784 long length vectors, right? So instead of having a square, we have a vector. So we just flatten this out. So this cell here just takes the MNeast train images and it converts it into these vectors of size 784. So we have 55,000 images, each one of size 784. Simon, you have a question? Okay. And we have also 55,000 labels. So for each image, 55,000 images, we have 55,000 labels, okay? If we would print out the first image, so I take the images and I print out the first image, this is what I will see, right? Do you guys see the difference with what I have been showing you in the lecture slide? What is the difference, Simon? What is the difference?
So it looks like it is not a square.
It is not a square. Yeah, absolutely.
Yes,
Doesn't
so
look like a square.
Number of rows is not 28 and the number of columns is not 28 in this representation.
Yeah, it's
but
actually
this
the shape is 784. So
yeah,
it's a
so
vector.
this is vector.
Yeah. What else? What else do you notice, guys? Kenneth, what do you notice?
The color values are from 0 to 1 instead of 0 to 255.
Exactly, exactly. So the color values are not 0 to 255. They're from 0 to 1. And this is a normalized version of the data set. So it's the same data set with 255. It's just they were divided by 255 just to normalize the values. Okay, this is the way how it's usually done in machine learning to kind of normalize the initial input values. But that's a good notice. Thank you, Kenneth. This is exactly what I was hoping for. Yeah, so there is a difference, but it's not too major difference. Here we can plot the first image. So I just saying I'm reshaping. So you can see I'm actually taking this vector of 784 and I'm reshaping it to 2828. You can ask me, why did you do that, right? You just converted them into vectors and now you're converting them back. What's the point? Well, I can tell you the point is that in machine learning algorithms, we're going to use the 784 vector long instances. But in order to visualize them, I actually need to make them matrices back, right? I need to make them matrices again, and 28 by 28. Now I can just play around, so you guys can play around and you can visualize more images. There are 55,000 images, so you can basically type any number that is less than 55,000, and you will get something out of it. And so please play around with that. And you can find some weird shapes. I'm pretty sure if you type long enough, you will find something that looks weird, like this 6, for example. I don't think it's very nice way of writing 6. Well, most of them look okay. Most of them look okay. So if we go back to the first digit was 7, you guys remember that Python starts to count stuff from 0, not from 1, as normal humans do. That's why I personally like R more than Python, because R starts to count with 1, but Python starts to count with 0. So let's see what's the label. What is the label of the first digits of this digit? And surprise, surprise, it's 7. Right, that's very magical, unbelievable, right? It's 7, but that's just the way how you can match the images and labels, right? So you have labels and you have images, all that. Here, it turns out that operating with 55,000 or 60,000 examples is not very easy. It's not feasible at some point. So we have tons of data here, but since this is just an educational example, we wouldn't use all 55,000. We are going to use just 2,000 for training and 1,000 for test set, right? In real life, of course, you shouldn't really just discard like 90% of your data, but in this specific example, we can allow ourselves to do it because, well, it's just will take a lot of time if we use all of these images, right? So what we do, we just say that first 2,000 images will be train images. First 2,000 train labels will be train labels. And from 2,000 to 3,000, this would be test images. And the same would be test labels, okay? We can plot the histogram. So we plot the histogram of the training labels. Basically, every bar is showing the number of labels of a specific class. For example, the first bar show us the number of zeros in the data set. The second bar show us the number of ones in the data set, and so on. Igor, what conclusions can we make from this histogram? Looking at this histogram, what is the first thing that comes to your mind?
Actually, nothing.
Nothing. All right. Fair enough. Fair enough. Okay. On your second thought, what could you be looking for if you would be plotting the histogram of labels in your training data? What is it that you might be interested in?
We might be interested. Is it?
Wait.
Okay.
Igor, what you're saying?
Well, actually, maybe I would like to understand what is maximum and minimum, and what's the difference between them.
Maximum, minimum. Okay.
Yeah, so I mean in like 3 and 5 in terms of x.
Okay. Okay. This is interesting. Oleg, what you were saying?
I think we would be interested if it's balanced or not balanced data set. Yeah, if it's
okay.
For example,
okay.
we could have no value for 0 or 1 value for 0 and 200 for 8. Yeah, then it's really not a good balanced data set.
Yeah, this is what I was looking for. I think, Igor, you were trying to say something of a similar kind. So basically, these are how many examples of zeros we have, how many there are data points of class 1, and so on and so forth. So basically, it is interesting to us to see that most of the classes are well balanced. So they're pretty much all data set does not have missing classes. Like, for example, there might be a case where we wouldn't have any images of class 0, for example, or there would be too many classes, instances of class 8. There are too many 8s, for example. So this is something that we are interested in, because otherwise we would have a very skewed performance of our classifiers. Igor, does it make sense?
Yep, absolutely.
Okay, sure. Do you want to ask any other question? Okay, cool.
No.
Anybody else wants to ask any questions about the histogram of classes? So this was just an exploratory data analysis. I think something that you have done with Roman Ko for some time. Okay, just looking at the data set and seeing whether it's balanced enough or something like that. This cell here, if you run this cell, you will see some examples per class. So these are the types of zeros that you have. These are just the random examples of zeros that you have in your data set. These are the random examples of ones that you have in your data set, and so on and so forth. Do you guys see something weird in my screen? Any weird examples that you wouldn't consider to be something that belongs to that class? How about this 4? How about this 9? Well, actually, it's 9, but it looks like 4. At least to me, it looks exactly like 4, right? So this guy here. What about this 7? So this is 7. How does it look like 7? I don't think it's 7 anyway. And you know what? There are plenty of this kind of examples all over the place. For example, this is 0. This is 0, but it actually looks like 6, and so on and so forth. So it's going to be a tough job. So it's not easy. Now, what I want to ask you is, so looking at my lecture slides where we have discussed the Euclidean distance, you remember what the Euclidean distance is? Lena, what's the Euclidean distance? How do you calculate the Euclidean distance between one point and another point?
Like you need to x2 minus x1 squared, like
squared
and plus y2 minus y1 squared, and something like this.
And the last bit, that's the last bit, just to finish it up. What is it? The last thing? Oh, it's all good. It's all right. It's just the last thing that's missing.
Корень квадратный.
Squared root. Yeah, the root, square root of this number. All right, so could you guys, so this is a small exercise. You have two images, image 1 and image 2. Could you please find Euclidean distance between these two images and write it here, write it here. So you have image 1 and image 2. What I'm asking is, could you find Euclidean distance between image 1 and image 2? Think about this in that way. So you don't have x1 and x2, and you have x1, x2, x3, x784. So you have 784 dimensional space, but you don't really have to care about this, because all it takes is just to write image 2 minus image 1 to get the coordinate-wise difference. So just start from here and add more to this to calculate the Euclidean distance between these two images. Lena just gave us the formula. She just told us the formula. So just go ahead and I give you a couple of minutes. Please raise your hands as soon as you've done it, okay? And if you have done it, test it yourself here. Test it yourself by running this print statement here. If it shows 11.858, it means that you have coded it correctly. If it shows something else, then there is a problem. Just take it as a challenge. Igor, that's the challenge you were looking at. So that's your challenge. Or it's not a challenge anymore. You've done it. Solve that.
It's challenge, yeah.
Go ahead then. Go ahead. You're welcome. I'm sorry. I'm being a bit pushy, I guess, but.
No, it's cool. I don't need any challenge anymore.
No, that was too fast. That was too fast. I got too many more challenges ahead. So please deepen your appetite for challenges, because we'll have more to come. Please raise your hand as soon as you've done it, so that I know that there is at least, so we can, slowly start to work with that. Just to, I'll just write comments here. So this is coordinate-wise difference squared. So a sum of coordinate-wise differences. Okay. Oh, sorry. A sum of squared coordinate-wise differences under the square root of SQRT, under SQRT. So each difference is squared, and this is summed up, and then you have a square root above that all stuff. Raise your hands as soon as you have done it. Sup. Okay, Lena done it. Great. Quick, fast. Keep your hand up so that I can see that. I can see that we are filling up. Okay, so first one is there. Lena is, what's the time now? It's
like 4 a.m.
4 a.m. Oh, that's a very right time to study some machine learning. I understand. Nobody's interfering, right? Yeah. So what is it? Let me start very slowly, maybe helping you somehow. So if you guys have image 2 minus image 1 squared, So I usually write squared like this. So you can use maybe a function or something like this, but I usually write squared like this. Then you can sum this up using NumPy. So you can write NumPy sum on top of this. And then you can take a square root, right? SQRT. And that should be enough, right? So this would be a squared sum of differences, coordinate-wise differences, under the square root, okay? I'll post this. So you guys, you have my screen open. You may have my collaboratory open. And if you feel like my code doesn't match your code, you can come back to my collaboratory. So open my collaboratory in your screen and just copy paste the same line, okay? Just to make sure that everything runs smoothly, you can copy paste the same lines, and then just to make sure that everything is okay. So let me copy this to the chat. Here we go. This is the line that I have. Elena, do you have something similar, or you have written it in a different way?
Yeah, it's a similar one.
Okay, cool. You guys, Igor, Kenneth, and Simeon, are you guys fine? Oleg? So if you have some troubles, please copy the same line, okay? Just copy it. I do really recommend, because I had a lot of students having troubles because they thought that, oh, I'll just leave my version because it looks nicer to me, and that makes sense. But sometimes they get some troubles down the road, okay?
I think another way could be to use least comprehension, yeah?
Yeah, the least comprehension is possible, but I think we should be trying to use this advantage of NumPy treating everything as arrays, and that makes it a bit faster. We will use least comprehension very soon because there is no way around it. But here we can use just the NumPy. Sorry?
No. So, whoa.
Does it work? So please, everybody, raise your hands if you see that your print statement gives you this print statement. So you can see the same print statement as I do here. So raise your hand if you see the same stuff.
I am cool. I am programmer.
Yay! Igor, raise your hand if you see the same stuff, please. Then I know that you're okay. Kenneth is there. Okay, you raised your physical hand, which is nice. Simeon, you're nodding, but okay, now you have a hand as well. Oleg, does it work for you? Okay, great.
Yes.
Thank you very much. Now, there is a little bit of theory again. So what happens is that we are assuming, ladies and gentlemen, this is very important. We are assuming that Euclidean distance between similar classes of images. So if we go back here, then we assume that the distance, Euclidean distance between onces will be smaller than Euclidean distance between, for example, 2 and 9. All right? So this is our assumption. This is what we assume, that the Euclidean distance between classes, the same classes, would be smaller than Euclidean distance between instances of different classes. And here I basically, I'm offering you to check that. So here I take the trained labels of one class. These both are 3s. And I calculate the distance. So these are the distances. Let me run this line here. So, okay, the distance between 3 and 6 in this data set is, for example, 10.8. The distance between 2 images of class 3, but they are different, is 8.07. So you can see that instances of the same class seem to be closer in Euclidean space than distances between instances of different classes. Okay.
I get a difference between 3 and 6 of nan, N-A-N.
That's because there is some problem with the distance function. So please copy the same. Make sure you copy the whole thing here and run it. Okay. Just come here to my collaboratory, copy the distance function and insert it into your cell and run the cell. And then we run this print statement and this print statements. Igor, do you have, is it all good for you?
Yeah, it's all good.
Kenneth, good for you? Okay, cool, cool, good. Now, so there is an algorithm. So this nearest neighbor algorithm, which goes like this: compute distances to all points in the data set, right? Find the closest point and report its label. So this is what we are going to do right now. We will use one test image. We'll use the first test image as the image for which we will be running the nearest neighbor algorithm. So here we go. Let's plot the test image. Let's see what is the test image. So the test image is image of 8. Although it has this kind of weird gap here, it's still image of 8, okay? Now, this is another classroom exercise. Can you compute the distances to all images using this awful list comprehension technique from Python? So you now have a distance function. Here is the distance function. And now you can use the list comprehension to compute all the distances. So just one more before you start. Oleg, what am I computing the distance to and from? From where I compute distances and to where I compute distances?
We compute for all collection, right?
Tell me the name of the variables, okay? So where we compute the distances from and to where we compute distances to.
Let me check. Okay.
Kenneth, can you help us?
Test image.
You're muted, by the way.
Distance between class train label 8 and the image test image 0.
So the first part, the second part is right. So between test image and
train images.
And train images. Exactly, to all train images. So let me start with this and let's code this together. Let's code this together. So what we do is that we do something. So here I just type something, okay? We will fill this up, okay? This will not stay here. This is a function that we will do, but just, I'm saying for image in train images. So this means that I take one image from train images one by one. And for each one of them, I do this something. So I do something for image in train images. What is it that I do? Simeon, what is it that I do with image in train images? We can't hear you, you're muted.
Oh, excuse me. So we can calculate the distance between this test image and versus the every image in the train.
Which is, in this case, what is the
image.
name of?
Let's say
image.
This
exactly.
is image, yes.
Exactly. You guys nailed it. You guys absolutely nailed it. So this is how it looks. We calculate the distance between test image, this guy, this 8, and each image in the train images. So this is how the list comprehension works, right? So we take image in train images and we calculate the distance to the test image. And we save the result into all distances, okay? So if I run this now, I will see a bunch of distances. I just outputted 5 distances, but there could be more. There are actually 55,000 distances. Oh, sorry. How many there are distances? Igor, how many distances there are in this all distances variable?
Well, I've just not 5. Yeah, 5. 6. From
wait.
5.
No, I just outputted 5, but I can output more than 5. How many there are in total? So
in train, yeah, just a second. In train, first, I remember 2000. Yeah. 2000,
yeah, because we subsampled it. Yeah, absolutely good. Great. This is I have a practice of throwing candies at my students in my classes. Lena knows, she a couple of times missed that. Yeah, so if it would be a physical, I would be definitely throwing candies at you, but I'm sorry, guys. So the only thing I can throw at you is my beams of my positive and absolutely love and that kind of stuff. So what happens now is that we have distances, right? So these are the Euclidean distances from test image to every train example in our data set. Now we need to know what is the smallest distance, what is the image from the training set that has the smallest distance to our example. Kenneth, how can we get that? How can we get an index of the smallest distance in this all distances variable?
You sort and then just find the lowest one, or
yeah, that's another way. You can also use argmin. So this is a function that that just gets you the index of the smallest element. Okay, the index of the smallest element. The problem with the sort. What is the problem of the sort? Ladies and gentlemen, what's the problem with the sort? Sort is great because it will give you the smallest distance, but it will lose something important.
ID of the image.
Exactly. We won't know what image it is, right? What's the ID of the image? So in this case, with argmin, we will know the ID of the image. So I just I assign this ID to I. Lena, how do I get the predicted label right now? So I have the index of the training example that had the smallest distance to our test example. How do we know what's the label?
Labels.
It's not exactly labels, right? Because it's train labels.
Train
Right?
labels.
Yeah, and then what?
I+1.
No, it's actually I. It's just
I.
I because all distances is exactly the same dimensionality as train labels, so we can just type I, and that should be it. So if you run this now, this should give us the label of the predicted class, right? So just one more time, what we have done, we calculated all the distances. We figured what is the ID of the image with the smallest distance to our test example. And now we took the label of this training example that has the smallest distance. Here we go. So we predicted the class for the first image, which is 8. So this is the test image. So this is the test image that we were looking at. And the true label is 8, which is what we know anyway, right? We can visualize this predicted image, right? So this is the predicted image. So this is image, which class we used as a prediction for this image. Okay. Does it look similar to you guys?
Yep, sure.
So it had the smallest distance to this image in the entire training data. In the entire training data, this image was the closest, which makes sense, right? Now, can you please make a function out of these lines? So these lines here and there, can you please make a function here? Just copy paste the correct lines and make a prediction so that given image, you can also get a class that is predicted for this image. You can use training images as a, like a static variable. You know that the training images and train labels exist up there. So you can, you don't have to pass them as parameters, just use them as given. I give you a couple of minutes for that, and raise your hands if you have done it. And of course, ask me questions. If you feel like something is unclear, please ask me questions. So you need to first calculate all the distances, and then you have to calculate the prediction. The prediction is a class, right? So this is a class, not an image, but a class. And you have done, if you have done it and you want to test it, you can run this line here, the print statement. It should give you the same stuff as we have seen here, right? So the same stuff. Oleg, any difficulties? What's the difficult part?
To put all together.
Yeah,
So,
yeah. Kenneth, does it make sense for you?
Yeah, I'm trying to make, again, the same thing, trying to put it all in one
Yeah, in the same function, right?
in function. Yeah.
I can see that Simeon has done it. Congrats on that. Leno, are you there? Oh, yay. No problem, no problem. Don't worry about this. Igor, how far you are? How far are you?
Well, actually, I've inserted everything in one line, but and actually I'm trying to check it, but computer is executing.
Okay.
I'm not completing the.
So let me start. Let me start myself first. So we need to copy this part to calculate all the distances, right? So we compute here all the distances. But the problem is there is one important caveat. Oleg, what's the important caveat with this part? So I just copied.
You mean trap?
Yeah, the trap. What is the trap?
The trap that we already have this argument image.
Exactly. So this is not test image anymore, but image. And this should be renamed somehow. For example, train image. Send train image. For train image in train images, we do this, find distances to image to train image, okay? This is important because otherwise you would get a mess there. Now, what we can do is we can use train labels. This is where we're gonna take the prediction class. Kenneth, what should I write in here? What should I write inside the square brackets here? What should I type there?
The NP argmin all distances.
Yeah, absolutely. So that's the thing. I just typed NP argmin, all the distances, and here we go. That's the prediction. That's all you need, all there is. Please copy paste this code if you feel like your code is somewhat different and it doesn't work. So let me run it just to show you that it works. So we have predicted class for the first image is 8, and the true label is also 8. Makes sense, right? Oleg, did you get it?
Yes.
Okay. Kenneth, does it work?
Yeah, I had it in 3 lines instead of 2, but yeah.
Doesn't matter. It's perfectly fine. It doesn't really matter. I think 3 lines is even better because it's more readable. So you don't have to make it in 1 line or 2 lines, whatever. Just make it so that you understand. Igor, how is it going there?
Okay.
Okay.
Yeah.
How bad is it?
No, it's okay. No, it's really okay. So.
Okay, you copied or you made yourself your function runs right now. Okay.
Yeah, I've made myself, but some.
Okay, then just copy from my code. Don't worry about this. Just copy from my code. I wanted to show you the way how the homework exercises will be posted. Okay, so this is the first homework exercise. You will find a bunch of these homework exercises. So for example, this is homework exercise number 1. There is a homework exercise number 2. If you scroll down, there is a homework exercise 3. There is a homework exercise 4 here. And this is a homework exercise 5, right? So this is, okay, there is also 6. So these homework exercises are embedded inside the collaboratory. So they go as a flow, right? So you guys can, you can just, by executing all the cells that we have been working during the class, you should be able to understand what the hell am I asking from the homework exercise. For example, in the exercise number 1, in the homework exercise number 1, I ask you to implement K nearest neighbor, okay, K nearest neighbor, which is more difficult because you need to take into account K predictors, right? So there is only one popular version of the nearest neighbor. It's called K nearest neighbor. And the difference in algorithms is that we compute distances to all points in the data set. Then we find K closest points. And then we report the most popular label from these K labels, okay? So what we could do, we could implement this function here yourself. This would be the first homework exercise. So you can just implement it with you in the class, and then we can move on for the lecture and the exercises. So let's do the first homework exercise together here with you. So I'll give you another. So take off your raised hands. I'm taking off your raised hands. Think about this and try to implement this classify KNN function yourself first. So give you some time. Try to try to use Google and Google these functions like arcsort and bin count, and try to implement this function KNN yourself. Lena, are you fine?
Yes, I think
You're
fine.
sleepy. You want to sleep, I guess. Why didn't you? Yeah, it's weird. Weird.
Okay. It's fine.
At first, I thought that Kenneth is in Canada, and because Romanko told me that we have a student from Canada and they wouldn't be able to join online, and I was like, okay, Kenneth probably sounds like a Canadian name, so he must be in Canada. But then I realized that it's actually Lena who is in Canada.
Yes.
So I'm seeing that this could be a little bit too complicated to some of you, but it's also a good exercise just to play around with the code and see if you can manage it yourself. Did you have any programming exercises before in other courses?
Yes, but they're
Yes.
the space between the programming is like just enough that you can't remember what you're doing again. I have to,
Okay. Okay.
I'm trying to think, like, when was the last time I did Python stuff? It's been a while.
Okay. Okay.
The last professor decided to switch to doing everything in Excel for some reason.
Oh. Okay.
Yeah.
This course is purely Python based. So most of it has a good reason for that, because most of the machine learning and deep learning these days is done using Python, NumPy and Pandas and all that kind of stuff. So it's mostly Python. So if you ever do machine learning, then most probably you're going to do it in Python. Also R has a lot of machine learning functionality. I personally love R and I do a lot of R, but it just happened that on industrial level, people prefer Python. I think R is mostly used by researchers like myself, and they do research like physics, biology, and that kind of things. Yeah, so let me start slowly. We can take the same function from here. So finally, we have the same stuff. So image, train images, all is nice. But now we need to add a couple of more lines here. We need to add a couple of more lines. So what the lines that I would love to add is key and then okay, we can write them closest neighbors or nearest neighbors, if you like, nearest neighbors. So I proposed to use something called arc sort. So what it does what Kenneth has been proposing in the beginning, but instead of sorting the original array, it sorts indices, right? So it gives us indices in the sorted order, in the order that is sorted based on the values of these indices. And so let me show you how can you debug these things, ladies and gentlemen. I guess you can raise your hands from your computers to my computer, and just follow me for a sec, okay? Let's do it all together. Let's do it all together. So let me show you how I do these kind of things. It's not perfect things, so I must admit that I'm not a professional programmer, Python programmer, but I do have some experience. So let me show you how I do this kind of things. So when I have a new stuff that I don't know what exactly this NP arc sort does, I usually do something like this. I do return some dummy variable. For example, I just say prediction equals 0. I don't care about the prediction. And now when here I just insert the print statement and I say, hey, let's print out what are these nearest neighbors? How do they look like? And let's, just in case, print out not all of them, but let's say from 0 to 5, just to make sure. Okay, so I run this stuff, then I can add a cell by just pressing this code here. And then I can say, all right, so I will use k equals, let's say 1 or 5, let's say 5. And this is a printout of my function, right? So I print out nearest neighbors, 5 nearest neighbors. So these are the indices. These are the indices of images, train images that are closest to my test image. Does this make sense, everybody?
Yep, no, this is good.
Okay, so now if I want to have k nearest neighbors, what should I type here? Simeon, what should I type if I want k, specifically k, not 10, not 5, not 6, but k?
Let's specify the number we'd like to take, 0 to k.
0 to k, exactly. I want k, so here I am. So if I say that, so this should be like this. So I should get exactly k nearest neighbors. So let me run this. And it's again 5, but if I change this k to 10, let's say, then I should have 10 nearest neighbors, right? These are indices of the images that are closest to my test image. Now, that's great. What can I do now? Igor, what can I do now with these indices?
Well, you can take I think smallest one. No?
So what are these indices? Can you tell me again, what are these indices?
Well,
what do they represent?
They represent from smallest to highest all distance, they represent from smallest to highest, I think.
So these are
IDs of trained images, yeah.
Exactly, IDs of the images. So if this is the image with the smallest distance, right? Then this is the image with the highest distance, but these are just 10 nearest neighbors, right?
Yep.
What can I do with these indices to get my class predictions? So I want to have classes instead of these indices.
I'll look at the labels and then see what's what.
Yeah, exactly. So let me see. So let me call it classes or predicted classes. And then I will do just this, or maybe somebody can tell me, or I can just type it, labels, and then I can say nearest neighbors, right? So what would be the predicted classes? Lena, what would be inside this predicted classes? So let me question it like this. So let me put it the question like this. If I run this line right now, what shall I see? What shall I see here?
Labels, train labels.
Like yeah, just classes, image classes, right? Like something like this, right? So 8, 5, 4, so on. So what can you guys say about this test image? What can you guys say about the prediction?
Probably an 8.
Sorry?
Probably an 8.
Yeah, so the majority class is 8. Now the final caveat is how do you even make it work? So how do I know which one is majority class by using programming, right? So the function that I have here for you is called bin count. So let me try the bin count myself. I don't remember it myself anymore. So let's try to print out whatever it has to tell us. So Igor, can you interpret what the hell this is? What the hell is this? So just a sec. Just give me a second. I'll print out this nearest. Oh, sorry, not the nearest neighbors, but predicted classes again to help you out. Okay. So okay. So now, could somebody interpret me this line here? What each of these values mean without knowing what exactly bin count is, just by looking at this line here. Igor, what do you think this 7 represents?
Oh, that's interesting. I see 7, 8.
Exactly. Exactly.
There
are 7, 8.
1, 4, and 2, 5. So it's
exactly.
It's a number. So bins means that first digit is like how many zeros in bin 0. Second is how many ones in 0, 1. Then 2, 3, 4, 5, 6, 7, 8. Yeah. So 8 bins, and we can take maximum number of the highest bin or something like that.
Yeah, yeah. I have another question. Kenneth, what do you think would be a number of these, what would be the number of these values if I would have, let's say, 25 classes instead of 8 or 9? What would be the size of this vector?
1 less than the ones that show up. So
yeah, yeah. So if it would have the highest class predicted, let's say 14, then the size of the vector would be 14, right? If it would be 25, then it would be 25. All right. So can you tell me what should I type? What should I type to make it final? So if I just assign it to the prediction would be a vector of 8. But what should I add here to make it one single number?
Well, we can display number of bins with the highest.
We have to display an ID with the highest value, right? In this vector. Lena, what would be the function that I should use here?
Okay, you need to, I don't know, count.
Count?
I don't know. Like,
let me explain it just one more time. So we have 0 zeros predicted, 0 ones is predicted, 0 twos predicted, 0 threes predicted, only 1 4 predicted. So here is this 1 4, 2 5 predicted, 0 6s, 0 7s, and 7 8 predicted. So what is the final prediction? Kenneth said it already. It's 8, right?
Yep. So like you need to find max. No, I don't know how to explain. Like
You need to find max. Kenneth, what is it
R?
that Lena is trying to say?
Yeah, it would like to print the value of the highest count of bin, whatever that. I don't know what that function would be though.
Okay, yeah. So it's remember argmin?
Argmax.
Yeah. So it's just argmax. Okay. So now if I run this line here, my prediction is 8. All right. So now that I can safely remove it, but since you guys, I have your pictures, I can't have it. Okay, now I have it. Nice. Okay, so now if I run this, I get, so predicted class for the first image is 8, and the true label is 8. And this is k equals 10, right? And these are the bin counts. I can also predicted classes. I can type predicted classes here, and then I would know what were the votes. What were the votes? Okay. So here in the B part, so this homework exercise consists of 2 parts. A part is about implementing the KNN, which is worth 2 points, and there is a B part. The B part is modifying the KNN function so that it outputs the K nearest labels, right? And this is what we have already done. These are the K nearest neighbors labels, okay? So we need to report 10 nearest neighbors for the test image, and this is what we have done, exactly the same stuff. And you should also explain the output in the cell below. So here you should just write what this is, okay? What are these stuff? This is the homework exercise number 1. Similar, you should do the other homework exercises. We will not do other homework exercises together with you, but I assume that you will be able to do it yourselves. Questions about homework exercises, about KNN, about Python programming, about the course, anything that you like to ask? Ladies and gentlemen, any questions? All right.
Nope.
Nice. Okay, so it means that I have been crystal clear. You understood everything. You're on the same page. Absolutely great. Now that, well, you don't have any questions, you can tell me how do I make predictions for all test images. So if I run this line here, I get a prediction for 1 test image. By the way, I should switch off this printing. By the way, switch off your printing, because if we do it for all test images, that's going to be awfully a lot of output. So please just comment out the printing statement here, just for this, for the time being. For the time being, put the hashtag in front of the print statement, just to make sure that you don't get tons of input, printing output as soon as you run it for all test images. Simon, how do I predict classes for all test images using our function KNN and k equals 10?
Yeah, let's use 4 to pass 1 by 1 through all the images in test image.
Can we use this list comprehension thingy?
Yeah, of course. Let's say,
yeah. So tell me, what should I type here?
So what we want to do, it's classify KNN. So yes, so KNN with 10. Let's take image. For image in we want for test or training. I forgot. Ah yes, test. for test predicted. In test predicted.
We don't have test predicted.
Test images.
test images. I'm your synthetic, what was it? Syntactical analyzer, and I'm saying that there is no test predicted. I'm sorry, I don't know that stuff.
Thank you.
All right, so yeah, please copy this, ladies and gentlemen. I'll just copy to chat, just to make sure that everybody on the same page. I think, Kenneth, what we discussed, the Slack would be nice because the Slack has nicer functionality for copying code. The chat is not so great here in Zoom.
Yeah, and all this chat disappears after we hang up.
Yeah, as soon as we stop the session, everything is lost. And
or if you lose contact, it disappears.
yeah, absolutely. So please type in this stuff and run it. And what is the observation that you can make? What is the observation? What do you observe? Igor, what do you observe? Igor, did we lose you forever? No, you're still there. So what was the, what kind of felt weird when we ran this line? We ran this line and it felt weird. Anybody?
No, nothing felt weird. It wasn't very fast.
It wasn't very fast. Well, that was my way of saying, did you guys feel it was slow? Why do you think it was slow? Why do you think it was slow? What's the major thing that makes it slow?
And number of K, in fact.
K is big, yeah.
K. Do you think K is the major problem? Oh, but let me disillusion you. I can make K equals 2 and it will still run pretty much the same time. And I can make K equals 1,000 and it will still run pretty much the same time. So
But
what makes it?
Because
it's running.
Okay.
No, go ahead. Just say it. Whoever was saying it. Oleg, you were saying something? Kenneth, finish your line of thought. What you were saying?
Oh, it's doing it in series. It's just like doing one after one after one after one.
Yeah. So, but there is a very important aspect of this algorithm that makes it very slow. Oleg, did you have what did you want to say?
No.
Okay, so what makes it slow is the pairwise distance calculation. So in order to find the nearest neighbor, you need to calculate distances to all the instances in your training data, which is at least 2,000 basically iterations of stuff, right? So you need to do 2,000 computation for each test image, and there are 1,000 test images. So for each one, you need to calculate 2,000 distances, which is basic math can tell you that is pretty much a lot. It's 2 million distance calculations, which is taking a lot of time. And so K nearest neighbor is criticized exactly because it's very, very slow. If you have ever studied complexity theory of algorithms, then you would know that this is a square complexity of the algorithm. For each one, so when you increase the size of the input, your time will square. So if you, for example, for 1,000 images, you waited for 1 minute, then or 2 minutes, for example, then for 2,000 images, you will be waiting not, okay, this is a bad example because the square is the same as yeah, so yeah, sorry for that. So if you were waiting, let's say 8 minutes, then when you take 2,000 test images, you will be waiting for, Lena, how many minutes? So 8 minutes for 1,000 images, 2,000 images would take you how many minutes? If it's a square, law is a square. So what's the first thing that comes to your mind? Like 16, right? That would be in case the algorithm would be linear. It would mean that whatever you add, it would just be linearly scaling up. But with the square algorithm, 2000 images would take you 64 minutes. Not 16, but 64.
Mhm.
All right, so any questions about this? Okay. Let's compute. So now we have test predicted. These are test labels. We can look of what it consists of. So these are predictions for each of the test images. And there are, how many there are test images, Oleg? So what's the size of this vector test predicted?
Please execute shape.
Please execute shape. It's 1,000 images. Oh, sorry. What is the problem? Length. Maybe this would work. Yeah, so it's 1,000, right? 1,000. There are 2,000 train images, 1,000 test images. How do I know how many of them are correct? So we have test labels. We have test labels, and we have test predicted. So we have predicted labels and test labels, the true labels. How do we know that? How do we know the number of correctly predicted labels? How can we compute the number of correctly predicted labels? Igor, how do we know the number of correctly predicted labels? How can we do it? How can we find out?
Have no idea how to automatically
find out which are the correct ones.
Yeah.
So what do you think will happen in if I run this line now?
Up to true false. So
yeah, so
we can calculate number of false.
We can calculate number of false or number of truths, right? So what are the truths in this vector? If I run this, I will get the sequence of truths and false. So what do truths represent? Oleg, what truths represent?
Truth represents that label from test dataset and predicted dataset the same match. Yeah?
They match up. They match up.
Yeah.
And the false ones mean that they do not match up.
Yes. Yeah.
So do you know what the numeric representation of true and false? What are the numeric representations?
0, 1.
0 and 1. Okay, so what if what happens? Who can tell me what happens if I write a sum? What happens if I sum true plus true? How much is true plus true?
2.
Igor,
2.
2.
2.
Yeah. What is the result of true plus false, Igor?
1.
1. False plus false, 0. So if I sum up, I'll get a number, which is 873, which would be a number of correctly predicted labels, right? This would be the number of correctly predicted labels. We can also divide this number by the number of test images to get something called accuracy. So accuracy is in our case is 0.873, which is basically this number divided by 1,000. And this is the accuracy. You have heard about accuracy, and accuracy is basically a basic measure to say how well you have done with your classifier, right? What is the best accuracy? What accuracy do you guys trust? So if I tell you that I have accuracy of that, you're like, oh, this is cool accuracy. Then you can trust that algorithm. What is that accuracy for you guys? Kenneth, which accuracy you will trust your business? You'll say, if you guys end up with that accuracy, you can deploy it in my business.
It depends entirely on the money involved and the risk involved, and doesn't matter.
Okay.
86% accuracy, it would be good if it was predicting coin flips. 86% accuracy would be bad if it was predicting survivability of haircuts, like it depends.
Okay, yeah, that actually makes sense. The segmentation problem that Oleg mentioned in the beginning, right? The major problem is that the pedestrian on the image takes up less than 10% of the space. So if you would have a classifier that predicts every pixel black, it would have a 90+ accuracy, which would be super dummy, right? It would be just having no useful information whatsoever. So in fact, my the answer that I was hoping for is that you wouldn't trust accuracy at all, any accuracy. In fact, none of it makes sense, because unless you really dig into what does it mean 0.87, as you yourself saying, depends on what? Coin flips, nice, fine. How about you know, segmentation of pedestrians on the street? Does 87 make sense? No, I wouldn't say that. I wouldn't say that, unless you really understood the other metrics that you have here. Do you guys have other questions about this? Okay, then what I propose is to check out how the misclassified examples look like. Igor, you remember we discussed this equal sign so that you can compare the test labels with test predicted. You can also get this the other way around. You can use the exclamation mark equal, and that would give you true in case they do not match up. All right, they do not match up. And this NP where is basically getting the indices of true elements of the vector. So this is basically saying, hey, give me all the indices of misclassified examples, all the indices of misclassified examples. So here I say, hey, show me the 10 misclassified example, 10th misclassified example. So let's look at the 10th misclassified example. And we can also see that it says that this image was 9. So this is a correct label is 9. And it was predicted as 7. And I think there is a good reason for why it was predicted as 7. So let's see other ones. Wow, this is awful, right? How awful is this? This image has 7, although it's very hard to believe, but it was predicted as 4. You can play around it. You can play around it a bit yourself and check out what are the others. So this one was predicted as 9, but it was 4. I wouldn't blame the algorithm for that. This one was 2, but it was predicted as 0, and so on and so forth. So you guys, you can see the source of problems. And the source of problems is actually this kind of very weird kind of looking shapes. But coming back to this 87 example, 87 discussion, I have more questions. Simeon, you have a MNIST data set, which has how many classes? Do you remember how many classes does MNIST data set has? So how many classes there are?
Which data set?
This data set that
this one, yeah. There are 10 classes.
10 classes.
Yeah.
Balanced. So what is the probability? What is the accuracy of the random classifier? How good we are?
It should be around 10%, I think.
10%, yeah. So we are 8 times or almost 9 times better than the random classifier. And since this data set is not unbalanced, it's quite balanced data set, we can say that the majority class prediction wouldn't get more than 10% either, right? So it basically says that 87 in this very particular data set case is nice. It's good. Yes. It's actually good. But as I was saying, you shouldn't trust accuracy. So one number, you shouldn't trust it. You should get more numbers to look at the problem and check out the data set, the unbalanced, and so on and so forth. All right, so this is a homework exercise number 2. What it basically says is that you guys should take a look at the at this function here that produces examples of classes and change it in a way that it will produce examples of misclassified images. So you would have, for example, in the first column, all the zeros which were misclassified as some other class. In the second column, you would have all the oneses which were misclassified as some other class, and so on and so forth. So you need to take that code for the second exercise here and change it so that it produces the output that you need. And last thing before we go back to the lecture, and in fact, before we have a second break, we can have this k-nearest neighbor classifier. We can use a scikit-learn library. I'm pretty sure you have been told about scikit-learn. Somebody probably mentioned scikit-learn before me. So scikit-learn is basically a treasury of machine learning. It has most of the things that you need for machine learning. Most of the time, you don't need to implement anything yourself. You can use just scikit-learn internal functions and be good about this. So here you initialize the k-nearest neighbor classifier with 10k, with k equals 10. I think they even have the parameter name neighbors, and they don't have you here. I have some, yeah, misspelling here and there. So this is the model with k equals 10. And then we can just feed this k-nearest neighbor onto the train images. And here we can use model.predict and test images. So we can say predict test images to calculate. Oh, sorry, this is model.predict, but it's, sorry. What I wanted to do was the model.predict equals test labels. So the same thing as we have done before, NP sum, and this would be the number of correctly classified examples. Yeah, basically model.predict. So if I would extract it from here, I would say that test predicted, and I could leave it up here. So instead of writing our own function called classify key NN, like this one we have done with you, then instead of doing all this work, you could have just written model.predict and then type what exactly do you want to predict, and that's it. That's all you need to do, right? So instead of having to do all that work, you could have done just model.predict. And what do you notice? Igor, what can you notice from the results of this scikit-learn library?
It gives me absolute number of good prediction, but it doesn't give me in percentage of goods out of bad.
Yeah, but I also, did you guys notice that they predicted correctly 863 images while we predicted correctly 873?
No,
Yeah,
I didn't recognize one.
I had different prediction numbers in my one too, actually.
Which one you had?
In my hand-coded one, it was 73 as well, so it was good.
Oh, the scikit-learn one also 873.
No, 863. Sorry.
Oh yeah, so that's the same as with me, right? So I also have 873 for my personal function, and scikit-learn gives me 863.
Regularization, yeah.
Yeah, no, I had 863 in my hand-coded one, which is.
Oh, you have 863. Okay. I think it's a random seed. Sometimes, let's go for a break and let's come back at 12:03 or 12:02, and then I'll ask you about what can be the difference between these two functions. Okay, go for a break.
Sounds good.
Okay, see you, bye.